Yeah, good morning, everyone. After the amazing concert and dinner yesterday, thanks for coming to this morning session about standard model and heavy ions. And we start with Didar Dobur from Ghent University on top quark physics.
Okay. Thank you, Andreas. It's a great pleasure to be here and represent my colleagues from ATLAS and CMS and present you top quark results we have obtained recently. So I guess we all agree that top quark is a special particle. With its Yukawa coupling nearly 1, the top quark is the heaviest elementary particle that we know of today. Its mass is an important parameter of the standard model as it enters in the loop through the loop corrections to Higgs mass and the W mass. And it has an impact in the stability of electroweak vacuum through these quantum corrections. It's the only quark that decays before hadronizing, giving us the possibility to access its bare quark properties. And top quark processes at LHC are excellent, provide excellent setting for testing perturbative QCD predictions. And top quarks can be also portal to new physics, and CMS and ATLAS continuously search for various new physics phenomena in top quark production and decay, mostly in the context of effective field theory. So back in 2010, we have been presenting, showing the very first top quark candidates we have had in our data, but since then, LHC has provided nearly 200 million top quark pairs to both ATLAS and CMS. And with half of that data, we have published more than 300 papers on top quark physics. So at LHC, top quarks are produced mainly in pairs through strong interaction. And depending on how W boson decays from top quark, we get 3 different topologies. Here I'm showing you a nice event display where we can identify 2 B jets nicely and 2 light jets from W boson, a muon and a neutrino in the form of missing transverse momentum. And identifying top quark events so nicely relies on heavily the identification performance of these objects, and we have had a lot of advancements in all these areas. Here I'm showing you 2 examples. On the left side, the B-tagging performance increase in the CMS and in ATLAS. We have, for example, increased background rejection factor 60 with respect to run 1 in our B-tagging performance for a given B-jet tagging efficiency. Okay, so the fundamentals, the cross-section measurements, we do that in every collision energy that LHC operates at 5 TeV, 7, 8, 13, and now 13.6 TeV. And the precision we reach is quite impressive, and we are currently way better than the theoretical predictions, state of the theoretical predictions we have at next to leading order QCD accuracy. We also perform detailed studies of differential cross-section measurements. At this conference, ATLAS have presented differential cross-section measurements in lepton plus jets channel, where they have focused on top kinematics and additional jet properties. They obtain, here I show you an example where they obtain a nice agreement between data and some improved theoretical matrix element plus Parton shower predictions. CMS instead presented a first study on the invisible part of the TT bar system, basically dineutrino system, where we use deep neural nets to improve missing ET resolution. And here you see the measured cross-section as a function of PT, sum of the neutrinos, where we see very nice agreement. In all this, and what follows, there's a continuous and very fruitful exchange between the 2 collaborations and the theory community facilitated by LHC top working group. Okay, the other process that we study in detail is the TT bar plus 2 heavy flavor jets. This is interesting for new physics effects, but also it is very important as it is the irreducible background for TT Higgs measurements, where Higgs decays to BB bar or CC bar or to multi-top production. It's a difficult process to simulate accurately as it includes 2 different mass scales. As you can see from CMS result and ATLAS result, where we compare to different matrix element plus Parton shower models, typically, the predictions are undershooting the data by roughly 20%. Some of the predictions in the new Atlas result do give a reasonable agreement when it comes to inclusive cross-sections in certain phase space, but looking at the differential measurements, also there they fail. So this kind of studies really help us to tune and scrutinize our simulations on this process, but all in all, it pays back directly in our other measurements like TT Higgs, which was presented at this conference. Previously, Atlas had here large discrepancies between data and simulation, but this is really nicely coming together now. The single top quark production through weak interaction is also studied in detail. I'm giving you one example, the TW process, which is interesting because it provides access to VTB and sensitive to BPDFs. The challenge here is the large TT bar background, and moreover, at beyond leading order, it has interference with TT bar. So it is quite difficult to separate this from TT bar background. Both collaborations use machine learning algorithms to do this. Here in the middle, you see the measured cross-section at different energies by CMS, and the last point is at 13.6 TeV. We also do differential cross-section measurements where we compare the measurement to different parton shower models as well as to the models where we handle this interference differently, and the agreement is reasonably okay. Atlas has updated their 13 TeV measurement. They improved the precision. They also measure VTB. It is not as sensitive as the other measurements we get from the other single top processes, but still a complementary measurement. We also study TT bar production in heavy ion collisions. Both CMS and Atlas have observed TT bar production in proton-lead collisions. These are interesting measurements because they provide information on nuclear PDFs at high X. Here you see a nice pure selection from Atlas on TT bar, and the measured cross-section agrees with different predictions of proton PDFs. CMS has also published an evidence in lead-lead collisions for TT bar production. Here you see a very nice event display, 2 B jets identified, electron and muon, which is a typical signature from a TT bar. And also here, measured cross-sections agree with different predictions. So this is a beautiful event display where which is a candidate for TT bar production with a Z boson, where Z decays to 2 muons, which has a mass very close to Z boson mass. This brings me to the topic where we try to measure all TT plus vector boson processes. All these processes, TTW, TTZ, TT gamma, these were observed for the first time at LHC. The TTW measurement from both collaborations come roughly 7 to 10% precision. They are agreeing between each other, but it is above the standard model prediction that we have currently. But here the difference is understood. And there has been also theoretical presentations at this conference trying to close this gap, taking care of the higher order corrections to these theoretical predictions. The TTZ has been measured down to 78%, and there we have nicely agreeing measurements with the theoretical predictions. Here I would like to highlight the latest measurement from CMS, where we measure TTZ together with TWZ down to 6% precision. Like in the TT bar and TW, here also they interfere at the next to leading order. We see roughly 2 sigma excess in data, and if we set the TTZ to its standard model value, we also obtain an evidence for TWZ, like you see in red here. We also perform detailed differential cross-section measurements for these 2 processes, where in this case we see some interesting deviation from the predictions. These TTV processes are interesting also because they are sensitive to effective field theory, the new physics effects modeled by effective field theory, and we do detailed studies. And here I'm going to show you one example in this context, which is the TT gamma measurement and its interpretation by Atlas, the photon can be radiated either from top quark or its decay products. And they have performed a measurement where they use machine learning to separate these two processes nicely, increasing the sensitivity to top photon coupling. And there we can investigate anomalous dipole couplings of top quark, which is absent in standard model. And this can be done in the context of effective field theory, where the photon PT as well as ZPT from TTZ have the most sensitivity. Combining these two, we get complementary sensitivity to these Wilson coefficients that model this kind of couplings. So this is TTZ, this is TT gamma, and this blue is the combination. At LHC, we also perform searches for very rare processes. Both Atlas and CMS have observed simultaneous four-top production. And here, the cross-sections measured by both collaboration also come 1 to 2 sigma above the standard model prediction. And for this process, it is also interesting because one of the diagrams that contribute has an Higgs boson, off-shell Higgs boson in the middle, which gives us the possibility to access Higgs top Yukawa coupling. But also, Atlas, with a new result, have used this diagram together with the TT Higgs, where Higgs is on-shell, to measure the Higgs width, relying on the off-shell production here, which is not as sensitive as the direct measurements we have done in CMS and Atlas, but still a complementary measurement. Top quark mass is a fundamental measurement in our top physics program, and over the past years there has been significant improvements here. CMS and Atlas have published more than 40 papers on top quark mass measurements. Here you see the list of top quark mass measurements and their value from CMS. At the top you see those measurements which are called direct measurements, which we use the cross-section dependence on the pole mass, and we extract the pole mass directly from these cross-sections, either inclusive or differential. The sensitivity we have here is slightly less. We have a reach precision about 1%. But the direct measurements where we use the top quark decay products give better precision. However, these are subject to additional systematic uncertainties when they are interpreted theoretically, because we rely on some non-perturbative simulations to model some non-perturbative effects. In this direct measurements, there are two subclasses that I would like to highlight. One is the boosted topologies, where we extract top mass from the boosted top jets, and these kind of measurements have been shown to have nice future prospects for increased precision as well as theoretical interpretability. The other type of measurements we perform is the case where we try to avoid using jet quantities, namely using the lepton from the W decay as well as either the soft muon from the B or J psi or the displaced secondary vertex, and extract the top mass from these two objects, which reduces the sensitivity to jet energy calibrations, but it is subject to different uncertainties like the fragmentation uncertainties. These are interesting because when it comes to combination, they help the total uncertainty to be reduced. Speaking of combination, CMS and Atlas have combined their run 1 top mass measurement. We combined 15 input measurements, 6 from Atlas, 9 from CMS. You see the results that we used here. On the right side, you can see the final result. The black dot is the combined final measurement, which agrees with the CMS only and Atlas only combination very nicely, and we have the top mass down to 330 MeV, heading to percent level, 0.1% level precision. These measurements are limited by B-jet energy calibrations. Having in hand such a large TT bar sample, we also go and do precision measurements on the Electroweak sector, namely measuring the W branching fraction and test lepton flavor universality. Here I'm highlighting a measurement from Atlas, where they have performed TT bar cross-section measurement in EE, mu, and E mu channels simultaneously, where they have fitted 10 parameters, one of which is this ratio of W decaying to muon to electron electron, the double ratio, in fact, where many uncertainties cancel out. The result is consistent with 1 with down to 0.45% uncertainty. This is the most precise value to date. And here you see the summary of the measurements, and in fact you can see that the CMS has also performed a similar measurement, also tau to electron, tau to muon, where all come with consistent with the lepton flavor universality, and we are not confirming this long-standing LEP anomaly. CMS also performs W branching fraction measurements. Here you see in the black cross, it also comes consistent with the standard model, not agreeing with the lab results that were obtained. We also search for charged lepton flavor violation in top quark production and decay. We do not find any significant excess. In particular, CMS has come up with a new result where they have improved their result by factor 2. And here we set limits on the top decay branching fractions to 10 to minus 6 to 10 to minus 8, depending on the structure of the interaction. We also search for baryon number violation and flavor changing neutral current, but these I cannot cover in my talk. They were covered in detail at the parallel talks. Now I'm coming to the last topic I wanted to cover, which is the spin correlation, polarization, and entanglement in top quark pairs. The top quarks at LHC are produced in unpolarized, thanks to the parity invariance of QCD, but the spins are strongly correlated. And the nice thing is that the spin information of the top quark is passed on to lepton or the down type quark. Namely, they are radiated preferentially radiated in the spin direction of the top quark. Then we can study these angular distribution of these leptons and the down type quarks and have access to spin information of the top quark. Namely, we can extract the polarization coefficients, the 6 polarization coefficients and the 9 spin correlation coefficients from differential cross sections. This was already done at run 1 and run 2 by CMS and Atlas, which are interesting also because the new physics can modify these spin and polarization structure. But what is new now is the fact that we have put some foundations of quantum physics to test, and that is what I'm going to cover in the next. So Atlas have come with a result where they have observed quantum entanglement in TT bar system, and then in a dileptonic final state, focusing on a low TT bar invariant mass. And CMS has confirmed this with, in the same phase space, in the same final state. But we have also come up, the CMS have come up with a new result in the lepton plus jets channel, also observes entanglement, but in a higher MTT bar region, which is quite interesting. The spin correlation of top quarks is a kinematic dependence. So in particular, MTT bar and cosine theta. Theta is the scattering angle of the top quark. So you can see the map here, the blue regions are the regions where we expect so high correlations that the top spins are entangled. And we can use Perez-Horodecky criterion to come up with a threshold to measure this entanglement. So these CNN, RR, KK are the diagonal elements of spin correlation matrix that I mentioned 2 slides back. Or we can come up with a very simplified parameters, D and D tilde, which we can extract from a single differential cross-section. Namely, we need to, in the dileptonic TT bar channel, we namely need to measure the angle between the 2 leptons where the lepton momenta are boosted to the top rest frame. So this is the result in the dilepton channel from Atlas and CMS. Here you see the data point that is measured in a mass range between 340 to 380. There are also measurements in higher mass ranges, which is 5 sigma, more than 5 sigma away from the threshold. This is the D parameter that I mentioned in the previous slide. D parameter that is above 5 sigma. And at the higher mass ranges, we do not expect entanglement, and you see that the data and the predictions are above this threshold as expected. CMS presents two sets of results. Because in this low TT bar invariant mass range, we do expect the effect from TT bar bound state toponium at a mass roughly 343 GeV with this kind of cross-section. We have added this samples to our TT bar sample, and we have repeated the measurement with and without. So at the top, you see the measured D value in the x-axis without toponium added in our simulation, and this is without the theoretical predictions without toponium, and in the bottom you see the with toponium. In both cases, data shows more than 5 sigma the entanglement, but adding toponium brings our theoretical prediction close to data, which is on its own very interesting. So the lepton plus jet channel has the advantage of having larger TT bar sample, I mean the larger branching fraction, therefore it's sensitive to high TT bar, MTT bar region, but the drawback is that we need to now access the spin information from the down type quark, which is difficult to identify, but here we employ the machine learning to identify this down type quark from W, where we succeed up to 65% of the time correct assignment. And then we perform profile likelihood fit to this cosine phi that we measure in various bins of MTT bar and cosine theta, the scattering angle of the top. And we measure the spin correlation coefficients and polarization coefficients in actually various kinematic regions. Here I'm showing you the inclusive one. But I think also the interesting to see here is that at this high invariant mass region, we have more than 5 sigma observation of entanglement. This is a region where, if one does the calculation, most of the TT bar quarks are space-like separated, which opens the prospects for testing Bell inequalities. But all in all, these open a new window to test several new physics models through entanglement. Okay, I think we can say that top quark physics is living its golden age. We have reached excellent precision in many areas. And the combination of ATLAS and CMS results proved to be powerful, and we have also observed quantum entanglement in top quark pairs, which is the first time of its kind at these high energies, by multiple analyses and different phase space regions. And I believe run 3 data will bring even more exciting results. Thank you.
Thank you very much. I see one question here.
Thanks for this whirlwind overview. Lots of results. On slide 20, could you show that, please? So I still struggle to understand what these parameters mean. For example, on the ATLAS plot, you have this D, and obviously the Monte Carlo describes it at some level, but quite different from the data. So what does that mean? Does it mean there is some entanglement in the Monte Carlos, but not at the right level? Or does this parameter have any physical interpretation? What does it mean?
Yeah. So thank you for this question, because it points to to an area where we have done detailed studies. It is true that the Monte Carlos seem to show less entanglement, but my colleagues at ATLAS have investigated this in quite detail. They have shown that there are sensitivities to different parton shower models. And that is why you see difference between the blue and the red. They are simulations with different parton shower models. But also there are some other effects. For example, here no toponium is included, which is supposed to be a pseudoscalar with a strong entanglement. That is one reason. There are a few other things that I think this can be improved, but there's, I think, other than these, there is no additional thing I can tell.
Thank you.
Some modeling effects.
Thank you. Yes, please.
Yeah, thank you for this very nice talk. I have a question. I'm a bit surprised that you stress so much this entanglement, in particular when you call it action at a distance. I mean, the point is that the tops never separate for more than a proton diameter. So why should I be surprised that you have action at a distance over a Fermi when we have seen action at a distance over kilometers in other areas? Isn't that a bit overblowing this expected result?
I think not, because this is something interesting. It got Nobel Prize. We also want to probe it in our high energy setting. But also it has been shown that these entanglement observables are quite sensitive to new physics effects in the context of effective field theory. So all in all, I think it is interesting, and it opens a new window. Now we can search for new physics using these parameters. You can have a look here. The authors have shown that they can reach to higher sensitivities in some EFT parameter space compared to direct searches.
Yes, one more quick question.
Hi. Yeah, I have a question to a different domain, slide 5 and 6, the TT bar plus BB. I was wondering, aren't there any higher order, let's say NNLO fixed order prediction for TT bar plus 1 parton, which one could compare to? So?
To be very honest, not that I know. Maybe Andrea knows better. I think not. Okay. These are all next to leading order plus parton shower predictions.
Yeah, I think there are new calculations coming. I'm not sure about next to leading order, but what we do have now is a combination of this 4-flavor scheme and 5-flavor scheme that is now possible in Sherpa. That is what we want to try next, but we didn't make it. They didn't make it on the plot for the conference in time because it only came out last week. But that's something that we want to study next, and we will also publish some distributions about that once this is available to see if there maybe the shapes agree a bit better.
Thank you. So let's thank Didar again. We move on to the next talk about standard model physics by Philipp Sommer from Dresden.
Yeah, thank you very much, and good morning. In the next 20 minutes, I hope to convince you that hadron colliders, and specifically the LHC, are an excellent place to do electroweak physics. And I start with a quick reminder that in the standard model, we derive the electroweak theory based on symmetry principles. So this is the SU2U1 gauge symmetry. The Higgs mechanism breaks the symmetry, and from this we get the W bosons, the Z boson, and the photon as the mediators of this theory. And the couplings, the properties, and the dynamics of these gauge bosons are predicted in the theory by just 4 parameters. And from this we can make predictions. For example, the theory relates the mass of the W boson, the Z boson, and the so-called weak mixing angle through this ratio, which is in the standard model predicted to be 1. Now, at the LHC, we produce these gauge bosons really in the tens of billions. And on the right-hand side, you see that we measured the cross-sections for these, for the production of these bosons over a wide range of center of mass energy. We also have results already at from run 3 at 13.6 TeV. And these measurements can be extraordinarily precise. So, for example, this reference here provides cross-section measurements at 5 and 13 TeV with a precision of just 1 or 2%. And it is these large event yields and the precision both in the measurements and in the theoretical predictions that allows us to test the electroweak theory, either through precise measurements using single electroweak gauge bosons, or we go to high energy where we produce multiple of these gauge bosons. And through these precision measurements, we are sensitive to a range of physics processes. So what's very typical is that we have these virtual quantum loops that modify the propagators of our gauge bosons. For example, most importantly here, loops of the top quark, or we can also have loops from the Higgs bosons, and these modify the measurable quantities. For example, it yields to this a small correction to the W boson mass. The correction is only 1%, but our measurements are 40 times more precise than that. Similarly, when we measure couplings, where we're sensitive to the weak mixing angle, we get modifications to the decay vertices. So this is shown here, and we measure effective weak mixing angles. Then, at high energy, we follow a different approach. So here, characteristic is that these processes involve interactions of the electroweak gauge bosons themselves. And such diagrams typically diverge with energy. This is shown here for the scattering of 2 W bosons. And you see, with energy, we get very large divergences. These divergences cancel exactly in the standard model through delicate cancellations between individual diagrams. And now you can imagine that if we have any deviations from the standard model, we destroy these exact cancellations, and this leads to potentially very large effects. And yeah, this mechanism we test in some of the rarest processes that we can experimentally access at the LHC. Now, first I want to talk about some precision measurements. Here, the measurement of the W boson mass and width released by Atlas. At the LHC, we measure this in leptonic decays of the W bosons to an electron and muon and the corresponding neutrino. And because of the neutrino, we can only reconstruct the W boson in the transverse plane. So we use proxy variables for the mass to obtain a measurement, for example, the transverse mass, or shown here, the transverse momentum distribution of the lepton. And overlaid in this plot, you see small variations of the W boson mass and width. And just looking at the scale here, you can understand that we need to understand this distribution at the level of just a few per mil to perform such a measurement. And we achieve this understanding through dedicated measurements. So here shown is a measurement of the W boson PT that we did in dedicated low pileup runs in 2017 and 2018 that offer a favorable experimental condition for the reconstruction of the neutrino transverse momentum. And together with progress on global fits of the proton PDF and also progress on theoretical calculations, this triggered us to revisit an older data set and perform a measurement of the mass and width. The W boson mass is measured with precision of 15.9 MeV. This is a 30% improvement compared to an earlier measurement on the same data set. And it is really facilitated by profiling uncertainties thanks to the better understanding that we achieved on the modeling. The measurement is in agreement with prediction by the standard model shown here in the gray band. Then we performed the measurement of the W boson width. So this is shown here on the right-hand side. The measurement is the most precise single experiment measurement of the width, and you find here that it's measured slightly high compared to the standard model prediction. Both CMS and LHCb have released measurements of the effective leptonic weak mixing angle. So this measurement we do in Z boson decays to 2 leptons, and the cross-section expanded in spherical harmonics are shown here. And you see here, there's a term that is linear in the polar angle of the decay lepton relative to the quark plane. And this parameter A4 is sensitive to the coupling and hence to the weak mixing angle. Now, at the LHC, we have symmetric initial state. So the only source of asymmetry at the LHC is the scattering of a valence quark with a C quark. This ambiguity resolved through proxy variables again, namely the boost of the Z boson along the beam axis. And this is shown in this plot by CMS. So you find in a given bin the asymmetry as a function of the reconstructed mass. And then as we go to higher dilepton rapidities, this asymmetry increases, and this is how we obtain sensitivity to the weak mixing angle. CMS measured the same asymmetry as a function of a slightly different variable. LHCb really has an advantage in the experimental setup in these measurements because they have precision muon reconstruction up to large pseudo-rapidities, so here up to 4.5, and this plot just shows you the acceptance of the detector in dilepton rapidity, where LHCb really covers the far forward region. This is compared to the green line, which is the central CMS tracking detectors, and CMS has put a lot of effort into an electron reconstruction, extending the electron reconstruction up to larger pseudo-rapidities. So with this, they can now cover the region up to 3.4. CMS, because they combine the central region and the forward region, can profile uncertainties on the proton PDFs. And this is shown here. If you compare the black markers with the green, you will see that this profiling reduces the uncertainties overall of the PDFs, and it also moves the results obtained with different global PDF sets closer together. And the measurement is shown here from CMS. The measurement is dominated by far by PDF uncertainties. So these uncertainties in proton structure are a large source of uncertainty for us. At LHCb, this uncertainty is smaller because we know the proton PDF better in the forward region, but LHCb has the disadvantage of running at lower instantaneous luminosities, so they have very large statistical uncertainties in comparison. And yeah, the results are shown here. The two measurements, LHCb shown for the first time here at ICHEP, measured in agreement with the standard model prediction. And yeah, the measurement by CMS is the most precise measurement from a Hadron Collider experiment. Then we already saw in the talk before measurements of WDK branching fractions. So these have historically relied on W boson pairs. What changes at the LHC is that the decay of top quark pairs is the dominant source of W boson pairs, and then by forming ratios we measure relative branching fractions like the branching ratio of the decay to muons to an electron, and this result was just shown by Didar, improves, or it's the most precise measurement on the market, and improves is even more precise than the current world average. Now, CMS has released for ICHEP a new result where they measure the relative branching ratio of the decay to a charm quark relative to hadronic decays. And this measurement is facilitated by using decays of the charm quark to muons. So here in this plot that shows you the reconstructed dijet mass, they tagged C quarks by identifying a muon inside a jet. And this gives a very pure sample of events shown here. And yeah, this ratio is then used, determines this value RC, which is 1/2 in the standard model if you assume unitarity of the CKM matrix, and the same measurement is also used to determine the CKM matrix element VCS. One more analysis I want to highlight is the production of tau leptons from photons. So here we radiate 2 photons from 2 protons, and these then proceed to scatter to tau leptons through this diagram. The experimental trick in this measurement is that the protons stay intact, or if they fragment outside of the acceptance of the CMS detector. And the characteristic signature then is that there are no particles reconstructed in CMS other than the decay products of the tau leptons. And you see the reconstructed charged particles in addition to the decay products of the tau leptons here, with a signal peaking here. This measurement is used to constrain the anomalous magnetic moment of the tau and the electric dipole moment, and it really dramatically improves over previous results in ultraperipheral heavy ion collisions. And the reason is that with using protons, I have a higher accessible photon energy, and this is even enough to produce particles at the electroweak scale, as shown here by Atlas, who measured the production of 2 W bosons from 2 photons. So then I come to high energy tests, and I'll start with new measurements of dye boson production in the first year of Run 3 data. And I particularly want to highlight the measurement of WW production, because this measurement is done jet inclusive, and if you know a bit the history of WW production measurements, you will understand that this is an achievement. Another thing I want to highlight is that the theory predictions we have for this, so in this lower part, we have a theory prediction at next to leading order, interface to parton showers, and this is indeed also the prediction that agrees best with the data. These measurements now routinely achieve a precision of 5% or better. And the latest addition to this is this measurement of WZ production by CMS that was presented for the first time in the parallels here. Generally, in Run 2, we have made a lot of progress in studying quartic electroweak couplings, and we can access these experimentally in these 2 processes. So this is vector boson scattering, where we radiate 2 gauge bosons from 2 quarks that then scatter, or we just produce 3 gauge bosons. And these are some of the rarest processes that we can experimentally access at the LHC. In the LHC Run 2, vector boson scattering has really been observed in all major channels, so this is shown in this plot. And overall, the agreement with the theoretical prediction is very good, even though these predictions mostly are only at leading order in perturbative QCD. Triboson production is experimentally more challenging because it's a non-resonant process, well, as the other, but it's lagging a bit behind concerning the number of channels observed. And I'd say we don't have a very clear picture yet if we agree with theoretical predictions. I just want to highlight 2 recent measurements, one by Atlas, one by CMS. So Atlas have measured the scattering of 2 W gamma. The way these measurements proceed is that in this case we perform a fit to a neural network discriminant, and from this we obtain the observation. Routinely, we now also perform differential measurements. So here shown the dijet invariant mass. CMS has published for ICHEP measurement of WZ gamma production. It's an observation from a fit to the Z gamma invariant mass. The measurement is slightly high compared to the theory prediction. As said, I don't think we have a very consistent picture yet of how well these measurements agree. And then we typically quantify the validity of the electroweak theory in these measurements in an effective field theory approach. So we expand the standard model Lagrangian with higher dimensional operators that we built from the standard model fields. And in these processes, we're interested in operators that only affect quartic electroweak couplings, and these enter at dimension 8 in the standard model effective field theory expansion. I want to highlight this result from WZ scattering because it illustrates a technique we use to impose partial wave unitarity on the limits that we provide. And in this particular case, we managed to, for the first time, to provide a unitarized limit on an operator that's only built from the Higgs field. So we start to constrain the Higgs sector with these measurements. A very nice study from CMS was done in WW scattering, where they studied the interplay of quartic gauge couplings or anomalous quartic gauge couplings and anomalous trilinear gauge couplings. You see here the same parameters shown up here, the same operator, and an operator modifying the coupling of the Higgs boson to the W boson. Now, the last topic I want to discuss is measurements of diboson polarization. And the reason this is interesting is that the longitudinal polarization states are generated by electroweak symmetry breaking. And asymptotically, the longitudinal polarization states, they behave like the original components of the Higgs field. So these are the so-called Goldstone bosons. The way this works is that we reconstruct again the polarization from the decay angles. So this is shown here. And we have already a history of measuring polarization in individual gauge bosons in diboson events. Now, what's new is that we also observed the joint polarization, so two longitudinal polarization states in diboson events. And this is measurements like this. So we classify events into decay angles of the two gauge bosons, transverse, longitudinal, and then have a neural network to discriminate the different polarization states, which are shown here in the solid lines. Now, recent progress here is that we obtained evidence for the production of two longitudinally polarized Z bosons. Again, a fit, in this case, to a BDT, and you see the red signal is the double longitudinal polarization. For WZ production here, we already started studying the energy dependence, and we have experimental access to values of the PT of the Z boson up to 200 GeV. Ultimately, what we really want to do is measure the scattering of two longitudinal W bosons. So this is the plot that I showed you in the beginning in the introduction. This was studied by CMS here, and the signal is shown in the magenta line here. You see that we don't necessarily have experimental sensitivity to this process yet, but it will be very important for in the high Lumi LHC, because it can help ultimately to determine if the Higgs sector is really a weakly coupled theory. So yeah, these polarization measurements are really a very active field in both the theoretical and experimental side. And I conclude here. So most of the results I've shown you have been released in the last year. So it's been a really good year to be an electroweak physicist. The key message from this talk should be that the LHC is competing with previous machines in electroweak precision measurements. And this is facilitated through a number of components that we heard a couple of times this week. Large data sets, we understand the detectors well. We have dedicated reconstruction techniques to do these measurements, and of course, we rely on state-of-the-art theory predictions. Presented to you new measurements of the W mass and the weak mixing angle. We have high precision measurements of the lepton couplings. And then the LHC tests the electroweak theory at very high energies in these very rare multi-boson processes. And these start to join the precision probes in the Higgs sector to help understand electroweak symmetry breaking. And thank you very much.
Thanks very much. Are there questions? Here's one.
Thank you very much for excellent summary of electroweak physics. So going to the W mass, yeah, which I would fully agree, one of the most important parameters of the standard model. So Atlas result, well, 15 MeV is very precise, but the majority of these results still obtained on data collected some time ago with much lower luminosities. So what are the LHC prospects for the W mass measurements with, I would say, newer data and all the way to high luminosity LHC?
Yeah, I mean, you can understand that this is a very difficult measurement. You have to understand the detector very well. When studying this process in high mu data, you rely even more on the theoretical modeling. So this is difficult. I don't know how I'm not in CMS, but I can talk a bit what I hear on the corridors. So CMS has put a lot of work in this measurement. I expect that this will appear very soon. I know the people involved in this are super meticulous people, and Maurizio wants to say something.
So our measurement uses 2016 data at 13 TeV. The pileup was not as high as today, but substantial. So in some sense, it's a very good proxy of what will be done in the future. It's coming. The technique is adapted in order to handle the kind of challenges that you're saying. So you see that we think it's a step forward.
Thank you.
Yeah. You were mentioning over here.
Thank you. Yes, please.
You were mentioning longitudinal W or vector boson scattering. Mm-hmm. Do you have in mind only the longitudinal polarization of the final state vector bosons, or are you also alluding to initial state longitudinal bosons?
I mean, experimental axis through the decay angles we get mainly on the final states. In these kind of signatures, what we can use is the fact that the polarization information is also encoded in the forward jets. In the end, it's a matter of definition, because the intermediate W bosons are virtual, right? What we will experimentally measure is the double longitudinal polarization of the final state. But there is some polarization information also in the forward jets.
Yeah, because for the initial state, I mean, there's very strong interference between transverse and longitudinal, so it's very difficult to actually extract longitudinal polarization for the initial state.
Yes.
Okay, thank you.
Sorry, I just want to make a comment about coming back to the WMASS, because I think that we're in a very good position with the WMASS, because both CMS and ATLAS are pursuing very different techniques, both with various pros and cons. So CMS is looking very much at the high mu data, which has a lot of power from statistics and so forth. It has challenges with the modeling, but I think those are many challenges that we can overcome. From the ATLAS side, we've also have more low mu data, much larger low mu data set than we had with the 7 TeV data sample at 2 center of mass energies. And again, those play the theoretical and the experimental uncertainties off each other. And so I think that between the two experiments and these different methodologies, we can really make very important statements about the WMASS in the years to come.
Thank you. Let's thank Philip again for the nice talk.
Okay, and we are going to switch to the heavy ion for the rest of the session, and we'll start with the experimental overview by Kai Schweda. So, please.
Yeah, thank you very much. It's a great pleasure to give this talk on behalf of the 4 LHC experiments. I would like to thank all my colleagues from all experiments for their kind support in putting this talk together. This goes beyond the LHC experiments. And I think it's timely to recap a bit of history. 3 weeks after the discovery of the charm quark, independently, a number of distinguished scientists came together and met to discuss what would happen if high energy would be distributed over a large volume. Large means much larger than the size of the nucleon, of the proton. And people speculated that there would be new exotic states of matter, that collectivity would evolve where all particles participate, and broken symmetries that are barely broken in the QCD vacuum might be restored. However, even 10 years later, the odds for this to happen were considered rather low. And today we have precise temperature calculations from lattice QCD on the transition from hadrons to quarks and gluons and on the chiral transition. And this meeting is considered, which was happening almost exactly 50 years ago, is considered as the starting point which ignited what is today a worldwide program, experimental program, with 2 colliders. These are the only 2 hadron colliders in the world. It's the relativistic heavy ion collider at Brookhaven Lab in the US, and of course the Large Hadron Collider LHC that collides nuclei as heavy as lead and where the beam momentum scales with the charge over mass ratio, so 82 protons over 208 nucleons in the lead beam. And here you can see beautiful events. We had the first long lead-lead run end of last year in September. It started after 5 years of pause. And here you see the beautiful event displays by the 4 collaborations. It's a single lead-lead collision, and thousands of particles emerge and are detected in the experiments. The low-energy program includes the S-Phoenix and the STAR experiments at RIC, and there's also NE61 SHINE that reported results at these conferences at the CERN Superproton Synchrotron. LHC has a fixed target program. They use the LHC beam that impinges on the noble gases on hydrogen in the smog system they use for precisely measuring the luminosity. And this allows us, the fixed target program of LHCb allows us to revisit forward production of hadron of heavy flavor with the new generation type of experiment. And you see the performance of LHCb. They already measured the Lambert polarization in proton-neon collisions, and it fits well into the world average. This is here you see excellent performance in the lead-lead run from run 3 with improved trigger capabilities, especially for the ultra-peripheral program. I will focus in my talk entirely on the LHC collisions, the high-energy frontier. And this is a cartoon of a heavy ion collision. It's actually a simulation. And you see in a collision of 2 heavy nuclei at high energy, a collision zone forms. And the temperatures in this zone are above several trillion degrees, where quarks and gluons can propagate freely over large volumes, and then the system expands, cools down, and decays into ordinary hadrons, which are detected by the experiments. And this expansion in the quark-gluon phase is subject to a fluid dynamic description with ultra-low viscosity, so there's very low frictional momentum dissipation, and you will hear more about this in the next talk by Magdalena. I will focus in my talk to show you how we probe this quark-gluon phase, what we call the quark-gluon plasma, by putting in jets, by looking at collectivity to study transport properties of the quark-gluon plasma. For example, the speed of sound is a unique property, a fundamental property of the equation of state. And we use quarkonia and their sequential melting to address the temperature. Though these 3 topics I will focus on in my presentation. So a jet emerges from a fast-struck parton that decays into a collimated spray of hadrons. This happens in vacuum. We are all used to it, all high-energy physicists. You put this in the quark-gluon plasma, and then the shower parton C, the free charge, they see the free color charges, and the medium induces radiation, and you see here, this is indicated by these springs, and this induced gluon radiation shows up at rather soft momentum at angles, at rather large angles with respect to the incident parton direction. And the question we now address is what happens, what's the response of the medium to this deposit energy? Is there a wake around the fast parton which follows the fast parton in the medium? And Alice has measured the recoiling jets that recoil from a fast trigger hadron on one side, and Alice measured the recoiling jet and pushed the measurement down to a very low momentum. And you see here the intrajet yield, the depletion, so below 1, the depletion around the trigger momentum signals parton energy loss in the medium, and the excess here at lower momenta, which is seen for the first time by this recoil technique established by Alice, is the medium-induced gluon radiation, and the calculations in implementing the recoiling jet and the wake are able to describe the data. What you see, if you look carefully at large momentum, there's a rise, but this is due to what we call a trigger bias, since the trigger hadron in the opposite jet also experienced, or the jet experienced energy loss, and CMS used photon deck jets to get rid of this trigger bias. So the photon tags the jet, indicates the energy scale of the jet, and escapes the quark-gluon plasma unscathed. And in this analysis, CMS defined 2 jet axes. One axis is called the energy scheme axis that points to the average flow of energy. So this carries the information on the soft part, for example, the medium response, aka the wake, and a hard axis, the winner-take-all axis, which points to the leading prong, the leading energy flow inside the jet. And these two axes might be further decorrelated due to interactions in the quark-gluon plasma, and this is quantified by this variable delta J, which measures the difference between both jet axes in azimuth and along the beam direction. And these are the results from the CMS collaboration. They investigated two different jet momenta, low and medium low, and you see the red is the PP data, blue the lead, and the ratios are shown in the bottom panels. They're normalized to 1, so they jump around 1, and the models, which you saw also in the Alice plots, are able to describe the experimental data. However, it turns out whether you have a jet or not is insensitive in the calculation, so this method seems not to be sensitive to the wake. Another jet result from CMS is shown here. It's the the energy correlations, the very first time this has been done in lead-lead collisions, just came out or was presented at this conference. So what you define, you define an energy correlator, and this energy correlator does the following. It looks for the direction of energy in one way. For example, you follow the jet, and then you look for another direction where energy flows. And if you set, for example, this exponent in the correlator to n equals 1, you are sensitive to the soft effects, for example, again, to the wake field or the soft medium response. And you see here the data, lead over proton, is not described by the models, so there's still work for the models and still new stuff to learn. So this is about the jets. Quarkonia was long ago suggested to probe the temperature of the medium. This means they start melting, and where the most compact, the most bound quarkonium is expected to melt the last. And Atlas has measured this. This is the PP result. You see the upsilon 1s state, the bound state of bottom and anti-bottom quark, and then the first and second radial excitation, upsilon 2s and 3s. And now in lead-lead, this looks totally different. You see the gray area is the larger combinatorial background, which you have at high multiplicities in lead-lead. And you see you can still see the upsilon 1s state. The 2s is already compared to the 1s state, heavily suppressed, and you barely see the upsilon 3s state. And the suppression is stronger for more central collisions, which is defined by for example, the number of charged particles or the forward energy. And the models are in agreement. So the green line is the upsilon 1s suppression, and these lines are the upsilon 2s, plus including the upsilon 3s states. And it's also consistent with the results from CMS. To address the speed of sound, the ultra-central collisions were used, so you trigger on the top one central collisions to make sure the volume doesn't change, so it's a constant collision volume, and within this constant collision volume, you look for a change in the mean transverse momentum, which indicates the temperature as a function over entropy. So the entropy is defined by the number of charged particles, and this is a prediction in these papers, and CMS has measured exactly this shape, and from that they extracted the speed of sound, which can be calculated from first principles in lattice QCD at an average temperature, which is given by the average transverse momentum, which coincides with the lattice QCD results. Now, Alice did a similar analysis, and they find if they use for the centrality estimator the number of charged tracks, they find a bit lower value. If they use the transverse energy, they find a bit higher value, and if they do this over different rapidity gaps, a similar picture emerges. So the question is still open whether this extracted speed of sound depends on the collision centrality estimator or whether there's eventually some not-known bias in the centrality estimators or in some of the centrality estimators. Elliptic collective flow is addressed in non-central collisions. You see here the collision zone. It's modulating in azimuth, and this azimuthal modulation is transferred into momentum space effectively in the quark-gluon plasma and quantified by the second Fourier coefficient with respect to the symmetry plane of the collision. Helium-3 is now available since in run 3, LHC operates at the high luminosity collider at 50,000 collisions per second. Helium-3 is 2 charges and has thus the 4 times energy loss in the TPC for ID, so it's a very clean signal, and we measured for the first time in ALICE the elliptic flow coefficient V2. It's very large. You see this goes up to 20-25%. And the control experiment was done by CMS a few years ago. And you see here the scale. Look, this is plus minus 1%. And the Z boson does not participate in the collective expansion of the medium because the Z boson, neither its decay daughters, if you look in leptons, see the free color charges. And ALICE is now taking 10 to 100 times more data than in run 1 and 2. The question where quark-gluon plasma formation sets in is addressed by looking at smaller collision systems. Here you see the example of proto-lead collisions left on from CMS on charged unidentified hadrons. And you see at high multiplicity in p-lead collision, this shows a similar shape, comparable magnitude, at least at high momentum, to peripheral lead-lead collisions. And ALICE did the measurement for identified particles. And again, the typical ordering of this elliptic flow coefficient, what is expected when you have fluid dynamic expansion from light, from the pions down to the heavier lambda baryons, is reminiscence of collective expansion. A complete different type of collision is when both nuclei are displaced from each other, that they do not interact, can only interact electromagnetically, and where the flux of quasi-real photons scales with the square of the charge number, of the atomic number of lead nucleus, which is 82. And then in this example, the photon splits into virtual QQ bar pair, which then interacts strongly with the other nucleus and is knocked on Mars shell, for example, in form of a J-psi meson. And depending on the photon energy, you have coherent processes where you probe the nuclear structure, and at high photon energies, you probe the subnucleon structure. This is an event display of an ultra-peripheral collision, completely distinct what you saw before for hadronic collisions. You see here the example from Atlas on the photon to tau lepton pair production. One tau lepton decays to a muon, the other tau lepton decays to 3 charged hadrons, supposedly pions, and this is the distinct event topology of an ultra-peripheral collisions. Almost empty detector, back-to-back soft track topologies, very easy to identify. And Atlas has used these collisions to measure the anomalous magnetic moment of the tau lepton. The photon couples to the magnetic moment of the tau lepton, and Atlas used particularly the PT dependence, which is especially sensitive to the magnetic moment, and reaches a precision which is comparable to the lab experiments. There's also data from CMS in lead-lead and PP collisions. ALICE has measured the gluon distribution, which shows strong suppression. This is the data J-psi production as a function of the energy in the photo-lead system. And there's a large deviation from linear superposition of nucleons, and also indicates gluon fluctuations or models in the incoherent process, the models which incorporate large known fluctuations of the gluon densities, so spatial fluctuations and local fluctuations of the gluon densities can better describe the model. So there seems to be hotspots in the gluon distribution. There's a measurement on the light-by-light scattering from CMS. I have to skip in terms of times. There is a new measurement on the omega baryon mass, 3 strange quarks, and the anti-omega baryon mass. The precision from ALICE is 3 times more higher than the present world average. And it's quite surprising. The entire world average is based on a total of 257 counts. And since the omega baryon mass is used to set a physical scale to all lattice QCD calculations, for example, lattice QCD might help to resolve the G-2 discrepancy for the muon by calculating at high precision the hadronic vacuum polarization, which is shown by this Feynman graph. So the final part of my talk, I discuss the future, the upgrades. So run 3 will stop end of next year, followed by 3 years shutdown called long shutdown 3 at LHC, where Atlas and CMS will install their high luminosity upgrades for the PP program. with improved, which will also help the heavy ion program. LHCb will, in long shutdown 4, which is scheduled to start in 8 years from now, will go to full centrality. Right now they reach up to top 30% most central collisions, and ALICE plans to install an entirely new detector, silicon-based, large acceptance, superconducting magnet. And I show this more. To get the highest precision pointing resolution, the tracker, the inner tracker, will go, a few layers will go into the beam vacuum, not exactly, there's still a protective vacuum like in LHCb, but it's inside the beam pipe, and the close position of the tracker will give first information on tracking 5 millimeters from the collision vertex, and that's an ultra mass or zero mass detector, 1 per mil, radiation length per layer with an record resolution of 2.5 microns, single hit resolution. And this will be, for studies into bulk properties, this will be arguably the ultimate heavy ion detector. And you see the detector has to go out when the beam is steered. Once stable beams are declared, it rotates in with an iris mechanics and to get as close to the collision point as possible. So the physics we want to address with ALICE 3 is the following. There has been a question yesterday in the plenary. We know the temperature from the transition temperature for measuring light quark hadrons up-down strange, and you see here the exponential tail of what the statistical model gives you, and a quark gluon plasma produces all hadrons at thermal yields. There's only one parameter essentially, which is the temperature, is 156 MeV, and this coincides with the results from the lattice. So this is the maximum temperature hadrons can live, and since charm is oversaturated, there's much more charm due to initial hard scattering. There's large enhancement factors at the same mass, and this gives ALICE access to multiply stranged baryons up to the triply stranged omega CCC baryon. And if this turns out to be correct, this would beautifully demonstrate that the charm quark, the heavy charm quark, can propagate freely over a large volume and is then subject to statistical hadronization. Another example of the ALICE 3 experiment is to address chiral symmetry restoration in the quark gluon plasma. Chiral symmetry is badly broken in the QCD vacuum. For example, chiral partners like the ρ1 meson and the A1 meson, they have identical quark content, but identical spin, but opposite parity. Their mass is vastly different in a quark gluon plasma. This would be restored. They would assume identical mass if chiral symmetry is restored, and ALICE wants to address this in ALICE 3. This will not be possible until end of run 4. It's just not enough statistics, and the new tracker will be the ultimate tracker to reject experimentally the large background from correlated heavy flavor production. So to point out, the Higgs field gives 1% of the proton mass due to it generates the small current quark masses. 99% of all visible mass comes from breaking of chiral symmetry in QCD. So I conclude, heavy ions offer a unique laboratory with an immensely broad physics program addressing all fundamental interactions in the standard model. I will not go through the details, but you can read the CMS and ALICE collaborations put out a review of the first 10 years, round 1 and 2, data taking. This is written, both reviews are written for people outside the field, for young graduate students or people who are interested. You can read chapter by chapter. They are beautiful reads about what we learned about QCD in the first 10 years. And the heavy ion physics program will continue, a vibrant program will continue with all 4 LHC experiments throughout as long as then LHC. So thanks a lot.
Okay, thank you, Kai, for this nice overview, and we have a room for questions. Okay, over there.
Thank you for the nice talk and nice introduction to this field. My question is about the speed of sound. Can you go to slide 15? Right. No, this obviously is nice results, but my question is, so this one the speed sound is not the direct measurement, right? So you need to measure some signal, and I guess you use some theory calculation then to determine the speed of sound, right? So can you elaborate how you determine these results?
Yeah, thanks for this question. So I was too brief. So the speed of sound shows you how the pressure changes with energy. So what you do is, it turns out, you take the logarithmic derivatives of the temperature with respect to the entropy. That's the equation. Maybe it's too hard to see. And for the temperature, as an estimate, we use the mean transverse momentum. This idea goes back to Van Hove 40 years ago, where above ISR energies, it was observed that the average transverse momentum is constant as a function of multiplicity. So this is an indication of the temperature. So that's the assumption. And the entropy you get here by counting the number of charged particles. The more charged particles you have, the larger the entropy is. Or you can take the transverse energy, and this causes the bias. So these are two experimentally well-known quantities. You can extract the mean transverse momentum in the collision, and you can count the numbers of charged particles. And from the slope, you get the speed of sound, or the square of the speed of sound.
Okay, another question? Okay, so maybe I will have one actually. So you show this energy-energy correlation measurement by CMS, and it seems that there is quite discrepancy between the theory and the experiment, which is actually, I think, something that we haven't seen for a while in terms of like a hybrid model, for example. So do you have some idea what's going on? Like, if there is what's the problem here?
I don't know. So this is the hybrid model is a model by Carlos Salgado. If Chris McQuinn is in the audience, we left. No, I cannot say more about the hybrid model. I'm sorry.
Okay, thanks. Okay, there is one more question over here.
You included the omega, the rho A1 interference.
Yeah.
Did you also consider the rho omega mixing in there?
No. That's a very good question. So these calculations, we would love to have more calculations from theory. It turns out there are very few people who can calculate this. And if theories would be interested in this, would be very nice. So, but this, I guess, will only enhance the signal and would be good to have these calculations, yeah.
Okay, we might have room for one more question. Over there.
In the lattice prediction, can they get that as a function of the rapidity also? You showed several results on the experimental side, but for the lattice you just showed one. I'm just wondering, are they able to, this is the speed of sound, I think.
Yeah.
Yeah, so,
yeah,
so can the lattice match, predict those other, make a prediction for those other ones also?
So, yeah, thanks for this question. The lattice predicts the speed of sound at a given temperature. The temperature is the average temperature coming from the measurement of mean transverse momentum. So if we tell the lattice community the temperature, they can calculate the speed of sound for any given temperature. So the answer is yes, I guess.
Okay, I think that we'll have to stop the discussion here, so let's thank Sky again.
Thank you.
And now we will move from experiment to theory. And our next speaker is Magdalena Djordjevic, and she will give the theory overview. So please.
Hello. First, I would like to thank the organizers for giving me the opportunity to give this talk. Today I will cover one important aspect of quark-gluon plasma research, and this is exploring the properties, bulk UGP properties in quark-gluon plasma. So QCD predicted that at extremely high energy densities, a new form of matter will be created. This form of matter, called quark-gluon plasma, consists of interacting quarks, antiquarks, and gluons that are no longer confined. And it is believed that quark-gluon plasma existed immediately after the Big Bang, which marked the beginning of the universe. Today, it can be created in ultra-relativistic heavy ion collisions in experiments RIC and LHC, and thus creating the quark-gluon plasma in these experiments allow us not only to learn more about the properties of this new form of matter, but also to learn more about the origin of matter at its most basic level. So here is a simplified scheme of ultra-relativistic heavy ion collisions. So first, heavy ions are accelerated to extremely large kinetic energies. Their energy is, their speed is close to the speed of light, so they will be Lorentz contracted, and they look like two tiny disks. Then they collide, and then they pass through each other, leaving behind them a matter of extremely high energy density. And if this energy density is high enough, quark-gluon plasma will be created. Then quark-gluon plasma rapidly expands and cools down, and its constituents, quarks and gluons, hadronize. And finally, these hadrons are detected in a detector. So by studying hadrons in a detector, we want to reconstruct the properties of quark-gluon plasma, and for that we need good probes. And it is largely considered that low PT particles, which consist 99.9% of quark-gluon plasma, are good probes to explore the properties of this form of matter. But now it is widely recognized that quark-gluon plasma has been discovered at RIC and LHC, and the current challenge is to understand its properties. And it was initially anticipated that quark-gluon plasma will behave as a weakly coupled gas. However, according to the current paradigm, quark-gluon plasma is a strongly coupled system, that is, it is nearly perfect fluid. And this then brings surprising connections between there is another system in ultra-cold Fermi gas, which also shows similar perfect fluid behavior. So there is surprising connections between the matter at extremely low and extremely high temperatures, that is between the hottest and the coldest matter on Earth. However, despite being very interesting, the question is whether quark-gluon plasma is a nearly perfect fluid, whether this picture is indeed realistic. First, the origin of low eta over S throughout the QGP evolution is unclear. The second thing, it is well known that for other substances, the eta over S has a minimum at the phase transition temperature, and then it increases with temperature. Then this paradigm of nearly perfect fluidity comes from hydrodynamics predictions and low PT data, and it was shown that these predictions are not very sensitive to eta over S, not far away from a phase transition temperature. So this all led to a question whether perfect fluid is too perfect, or whether this picture of near perfect fluidity of quark-gluon plasma is unrealistic. So to further study this, several state-of-the-art, motivated by this, several state-of-the-art Bayesian analyses were performed using viscous hydrodynamical models and low PT data to constrain bulk QGP properties. And here I will concentrate only on the eta over S. And I here show some representative examples. So in this plot, I show probably the most well-known, the one published in Nature Physics by Berhan et al. In 2019. Then there is a second one published in 2020 by Svizrev C. Then there is the constraint by JETSCAPE collaboration from 2021. And then if you look at this, we see that eta over S is relatively well constrained by Bayesian statistics in the low PT sector, in the temperature ranges between 1 TC and 1.5 TC, but it is weakly constrained at larger temperatures. And then there are latest Bayesian analyses that suggest that minimum of eta over S is not at phase temperature transition, but actually it is moved to higher temperatures, and moreover that it may even decrease with temperature. So this leads to a conclusion that after almost 20 years of QGP discovery, the eta over S temperature dependence still remains a puzzle. And this is one of the key questions about the properties of quark-gluon plasma, to which we still do not know the answer. So this is not the only question, there are many of them, but this is one of them. And the question is how to gain a new insight. So as I said, these previous studies were based on relativistic hydrodynamic predictions and low momentum data. And the question is how to provide a new insight, that is how to provide an independent data set and theory that can provide us with a further constraint on bulk QGP properties. And the main idea is to use high PT theory and data. So these are rare particles, and there is wealth of precision high PT data available, or that will soon become available at the dawn of the high precision era that is currently running RAN 3 at the LHC and S-Phoenix at BNL. And among them are angular average suppression of high PT hadron RAA, which is considered to be a good probe of high PT particle interaction with quark-gluon plasma. Since we have a general public here, I will just briefly describe what is RAA on a very simplistic example. So suppose that you have some initial momentum distribution of some particles, and then that each of these particles, when they go through quark-gluon plasma, each of them will lose half of its energy. After leaving the quark-gluon plasma, the final distribution will be given by this blue curve shown here. So then the RAA is defined as a final distribution divided by the initial distribution, that is a ratio of these two curves. Another important high PT observables are angular differential suppressions, that is high PT hadron V2 and higher harmonics V3, V4, and so on. And they are considered as excellent probes of QGP evolution. And again, on a simplified example, I will explain what is V2. So suppose that we have an asymmetric collision of two heavy ions, then the quark-gluon plasma will be created in the overlap region, and we see that this is asymmetric. It has an almond shape. And obviously, this quark-gluon plasma will be, as it is asymmetric, so the particles going in this direction will travel the shorter paths comparing to high PT particles traveling in this direction, and consequently, they will lose less energy in this direction than in this direction, so RAA will be different, and then V2 will be, in a simplified way, defined in this way. So these are considered as good probes of QGP evolution, and the question is how to use them to further constrain the bulk QGP properties. And the main idea behind the high PT QGP tomography is the following. So different bulk medium parameters will lead to different temperature profiles. So if you input some medium parameters into your bulk medium simulations, for example, eta over S, it will lead to different temperature profiles. And that is, the system will expand and cool down in a different way, and that will lead to a different temperature profile. And then these different temperature profiles can be directly probed by high PT particles, because when they go through the quark-gluon plasma, they will sense different temperatures, they will sense different path lengths, and consequently they will lose different amount of energy. And then we can generate predictions for these high PT particles probes, and then we can compare them with the experimental data, and through that we can infer temperature profiles that are consistent with both low PT and high PT data. And within this, we note that contribution to the energy loss is larger at larger temperatures, so they show larger sensitivity for inferring the bulk QGP properties at larger temperatures. On the other hand, low PT data are more sensitive near phase transition, but they are less sensitive at high temperatures. So these two present complementary tools, and due to this we conclude that high PT theory and data is powerful complementary tool to constrain bulk QGP properties. So performing state-of-the-art Bayesian analysis with both low PT and high PT data may enable us to better constrain the QGP properties and answer some of the key questions about the bulk properties of this extreme form of matter. And while this was recognized as a milestone by Jetscape collaboration, no decisive steps have been taken in this direction. And within our ERC project, our group has made some significant progress in this direction, and I will provide an overview of why this idea is important. So first, to have a QGP tomography, you need to have a reliable energy loss mechanism. There are several energy loss mechanisms on the market, but here I will just briefly overview the one that we use in our model. So this is our dynamical energy loss formalism, which has several unique features. So first important feature is that the energy loss has to be developed in a finite size, finite temperature QCD medium of dynamical particles, that is moving particles, and the reason of this is because in quark-gluon plasma, in heavy ion collisions, you generate a system which has a finite size and finite temperature. So then the energy loss has to be applied to both light and heavy flavor if you want to simultaneously generate predictions for light and heavy flavor observables and test them on a wide set of observables at the experiment. From our perspective, what is important is that within our energy loss, we don't have any fitting parameters in the model. That is, every parameter is fixed to standard literature value. And then the only input is the temperature, which is a natural variable in the model. And on the other hand, from bulk medium simulations, the temperature is the output. So the output from the bulk can come as an input in the model. So we tested the model against a wide range of experimental data. I will not go through that. And we show that with no fitting parameters, we can explain a wide range of data and even predict something. And then this leads to a good deal of confidence that we have a realistic description of part-medium interactions so that this model is suitable for QGP tomography. And then this is not enough. You cannot only have the energy loss. You have also to have a framework which converts the energy loss to what you observed in a detector. So I will not go into these details, but also if you want to develop Bayesian statistics and state-of-the-art exploration of QGP properties, you need to develop a framework which can include any medium evolution as an input. It has to be efficient, time-wise numerical procedure so that it can generate a comprehensive set of light and heavy flavor predictions to compare them with the experimental data, if needed iteratively for different combination of parameters, so that you can extract the parameters which are consistent with both low and high PT data. And we achieve this with the DRINA framework, where DRINA stands for Dynamical, Radiative, and Elastic Energy Loss Approach, and A stands for Adaptive or Arbitrary Temperature Profile. And now we come to the idea of QGP tomography, and if we ask whether really this works, whether these high PT particles are indeed sensitive to QGP properties and can probe different temperature profiles. And for that purpose, here we choose 3 representative and well-known examples of temperature profiles in quark-gluon plasma. All of them agree equally well with low PT data. So from low PT perspective, we cannot provide further constraint. But then we ask whether we can provide further constraint with high PT theory and data. Even by a naked eye, if you look at these profiles, you see that they are different. And for example, for this one, you see that the reddest color leads to highest temperature and the blue color to the low temperature. And you see that you have a lot of red in this profile. So you expect that if particles, high PT particles go through this kind of quark-gluon plasma, they will lose a lot of energy, and this will lead to the largest suppression or the lowest RAA. On the other hand, if you look at these profiles' evolutions over the time, you see that this profile upstairs is the most asymmetric. It looks most as an ellipse. This one is a little bit more round, and this one very soon become almost like a circle. So you expect that this one would lead to the largest high PT V2, this would lead to lower V2, and this would lead to lowest V2. And then we want to see whether this is really seen in the predictions. And then the predictions were generated, and we see, indeed, this gray one shows this middle profile, and we see that this middle profile really has the lowest RAA or the largest suppression. And for V2, we see that this upper profile has the largest V2, this middle profile has the lower V2, and this lowest profile has really very low V2, almost consistent with 0. So this leads to a conclusion that high PT predictions can indeed differentiate between different temperature profiles when low PT data cannot provide further constraint, and then it provides an independent constraint to low PT data and can be used together with QGP for QGP tomography. So I now come to the formal framework in which we, for the first time, include first steps toward including both low and high PT data into Bayesian statistics. And the framework is outlined here. So first idea is to change selected parameters on a grid. And then for each set of parameters, you run hydrodynamic simulations and generate low PT predictions, and then at the same time you generate temperature profile for each simulation, which will then be used, this temperature profile will be used as an input in the RINA framework for high PT predictions. And then you train statistical model on these predictions, on these low PT and high PT predictions, which you obtained for discrete parameters on a grid. And then through this statistical model, Gaussian process, you can generate observable predictions for provisional, that is for continuous values of investigated parameters. And then you can use Bayesian statistics on experimental data, either low PT, which are up to now generally widely used, or joint low PT and high PT. And then you can, from this, you can obtain parameter posterior distributions, and you can obtain, and then you can generate low PT and high PT predictions from this posterior to compare them with experimental data. And as a proof of concept, it is usually useful to use a small set of parameters. We have only 3 sets of parameters, so the thermalization time of coagulum plasma, constant theta over S, and norm. And for that, we generated latent hypercubes with 200 points with these parameters in these ranges, and all other parameters are fixed. And then for each set of parameters, we run the hydro simulations and generate predictions for low PT and temperature profiles for high PT predictions. And then after that, we repeat the procedure which was outlined on the previous slide, either for low PT or jointly for low and high PT. And here is shown only first for commonly used low PT inference. And these are marginal distributions for that Bayesian statistics. And then we generated from these marginal distributions, we generated the predictions for low PT data. So this is multiplicities is average PT for pions, kaons, and protons, and V2 for pions. And we see very good agreement with low PT data as expected. But then if we compare it with high PT data, so here are shown RA as a function of PT for charged hadrons and V2 as a function of PT for charged hadrons for 4 different centralities, and RA and V2 for one centrality 30 to 50 for heavy flavor D meson, we actually see a suboptimal agreement, especially for V2, where we systematically see an underprediction of V2 data. And then we can repeat the same analysis, but now much more complex, because we now have both low PT and high PT theory predictions and data, and these are the marginal distributions that we obtain. And if we now compare them with the same set of data, we see good agreement with low PT data, and we see also very good agreement with high PT data as well. And now if we compare these distributions, these blue ones are the ones which are obtained only with low PT optimization, and these green ones are obtained with both low and high PT optimizations. And we see that these 2 distributions are not inconsistent with each other, which is good. But on the other hand, inclusion of high PT data significantly narrows this distribution of parameters. And consequently, we see that high PT data can further constrain the bulk QGP parameters, and it is necessary for precision extraction of QGP parameters, and overall, jet tomography is crucial for such a purpose. So I come to my summary. I hope that I convinced you that unifying previously separated field of studies, low PT and high PT in theory, is actually very important for, to include them together in advanced Bayesian statistics, and that can significantly improve constraints of bulk QGP properties. High PT data from RIC and LHC were utilized for these purposes, and this approach enables their optimal use. And the question is, what do we need from experimental data at LHC and RIC in the high precision era to accurately extract QGP parameters? First, we need improved agreement between different experiments within the LHC, ATLAS, ALICE, and CMS, because it is very challenging to extract the bulk QGP properties if different experiments agree, the data with different experiments agree within large error bars. The second thing, we need precise measurements for high PTD meson, RAA, V2, and higher harmonics. And third one, we need, which is most important, we need precise measurements for at least B meson, high PT, RAA, and V2 data. And the reason for this is that due to heavy mass, big quarks, and consequent so-called dead cone effect, big quarks will lose significantly less energy compared to light quarks and charm quarks. And this will lead to qualitatively and quantitatively independent RAA and V2. And thus this provides independent variables which will lead to much better constraint of QGP parameters. As I noticed, model must simultaneously explain both low PT, high PT data, and within high PT data it must explain both light and heavy flavor, including B mesons, and that is why B mesons are crucial. And in conclusion, a joint effort, synergistic effort between theorists and experimentalists will be essential to precisely extract the properties of this extraordinary form of matter, and I'm very excited to the currently ongoing RAN3 at LHC and S-Phoenix at BNL. Thanks a lot for your attention.
Okay, thank you, Magdalena, for this nice presentation. We have time for a few questions. So there is one over there.
I have a question about the Bayesian inference method that you used. In general, you need a covariance matrix among the observables and a prior distribution for the parameters. What do you use for those?
So for prior, we use a uniform prior because we really didn't know. So this is the first study that was done. It was done only with 3 parameters, and because we use high PT data, we really don't know, we don't know anything in advance. So we didn't want to complicate with some known priors, we just use uniform prior. And for Bayesian statistics analysis, we used Hamiltonian Monte Carlo sampling because it turned out that it is much more efficient than MCMC in this case, and that is what we used. Thank you.
Okay, there is one over there.
Hi, Magdalena.
Hi.
Thanks for a nice advertisement of the results of your group. Well, so I have actually several questions, but to limit it a little bit, so you made a statement that low PT observables are kind of helpless to constrain properties of the QGP, but I think it's not entirely true because, for example, you're using initial state, you're using three different initial states. One of them, Monte Carlo Glauber, I mean, it's already been outdated basically by the low PT physics, actually.
Okay, no.
Yeah.
Okay.
The other thing is, my understanding is that you're looking only at 2 specific observables, the RAA and V2, and lots of analysis nowadays in jet physics, that's your field, right, is actually centered in the jet substructure measurement. So do you look at any jet substructure properties? I mean, there they actually talk about constraining the equation of state of medium by looking at the mass of the scattering centers, for example.
Yes, so these are 2 separate questions. So for one perspective, we just use RA and V2 because this is the first Bayesian statistics analysis that use both low and high PT data. And it would be very ambitious to start with something which has more than that. So in that sense, this is what we used. We plan to use higher harmonics as well, and that would be in the future. The second thing is these three profiles that I gave you, these are representative profiles, and yes, you're right, they are one of them is ruled out by the data, but it is ruled out for some different reasons. On the other hand, it agrees well with low PT data. And from that perspective, I don't say that low PT is useless. I never said that. It is very useful, but it is not useful enough to constrain the bulk QGP properties well enough. So you need to add something extra if you really want to constrain the bulk UGP properties. Otherwise, we would not be in a position that in 2024 someone comes with this kind of et over S, which I think it is really strange. If you get et over S, which can be at best consistent with constant temperature consistent with constant at over S over the temperature, this would be really strange. If this turns out, I would be really surprised, but this has to be independently confirmed by something else. And this is what I want to claim. We need something extra. And for other things, of course, other groups and other jet substructure can be used to explore different properties, and maybe we will be able to, I was just concentrating on one property, but there are many properties, and I just want to say high PT observables, both jets and single particles are very useful for such purposes and should be used for that. Thank you.
So unfortunately, we have to stop the discussion here, but you can continue, during the coffee break. But let's thank Magdalena and all the speakers again. Thanks a lot.